Assalamualaikum warahmatullahi wabarakatuh. Hello guys, welcome back to my channel. In this video, we will continue our discussion about static fluid. This is part 3. If you are first time visiting my channel and then this is the first video you see, I hope you can watch the previous one, part 1 and part 2, because this one the part 3 about static fluid. Before we start our explanations, you can subscribe my channel and then turn on the notification for updating other videos from me. Okay, let's continue our explanation with Archimedes Principle. In daily life, have you ever seen the phenomenon like this? Or like this? Okay, why the object can seems like fly at the surface of fluids and that condition at the surface of water? Yeah, because of there is something that push object upward. If object on the air, yeah, it will fall because there is a gravitational acceleration. But if the object on the water, it seems like fly. Yeah, it seems like fly. Why? Because the fluid gives force directed to the upward to the object. And then the force against the wake the object, and then it can seems like fly like that. In physics we call it float. Yeah, float. The magnitude of the lifting force applied by a liquid upon an object was first formulated by Archimedes. Okay, so the Archimedes is the first scientist that discuss about lifting force in the static liquid. Okay, and then Archimedes principle, he said that the apparent loss in wake of a body immersed in a fluid is equal to the wake of the displaced fluid. You can learn from the picture there. Figure 1.19 shows that the lifting force of the water on the object equals the wake of a floating water. Yeah, this one, the wake of object when the object on the air, yeah, is 30 Newton. So the mass here around 3 kilogram. Okay, this one the mass and the weight of object on the air. When we immerse the object on the water, in the water, yeah, we immerse the object in the water like that, and then you see the scale reading here show that the weight of object decrease. Yeah, the weight of object decrease, become 20 Newton. Okay, 20 Newton, and then the mass obviously become around 2 kilograms like that. And then when the object immersed inside the container, inside the water, and then there is water displaced. Okay, water displaced, and then there is a container for water displaced. Yeah, and then when we see the water displaced here is about 10 Newton. So based on Archimedes principle, the apparent loss in wake, yeah, apparent loss in wake of a body immersed in a fluid, yeah, apparent loss wake. There is wake loss, yeah, before is 30 in air, and then about in water is 20. There is wake loss, yeah, wake loss is equal to the wake the displaced fluids. Okay, displaced liquid. Why the weight of the object decrease? Because there is a lifting force. Lifting force here, or we call as FB. FB here is a buoyant force or lifting force. Yeah. Okay, this is by the fluids. Yeah, so the fluid has a lifting force, yeah, directed to the upward obviously, and then this one decreasing the weight of object inside the fluid. And then how we calculate the lifting force? The lifting force equal to the weight of water displaced. In here the weight of water displaced is a 10 Newton, so the lifting force is a 10 Newton. Yeah, we can see from the formula here, FB, buoyant force, is equal to weight of displaced liquid. Okay, if weight is a m times g, m here is a mass of displaced liquid times gravitational accelerations, and then the mass itself is a rho times v. Okay, rho here is a rho of liquid, and then v here, v of displaced liquid, the volume of displaced liquid, times g. Okay, and then we read again, this one very important. Since the volume of overflowing liquid equals the volume of object under the liquid surface, this is new for us, that the volume in here, yeah, the volume of overflowing liquid, yeah, the volume of displaced liquid here, displaced liquid, equals the volume of object under the liquid surface, or in here equal with the volume immersed. So the volume that immersed in the liquid, sink or immersed in the liquid, equal to the volume of displaced water or displaced liquid. Yeah, this is important. So we can replace here VB, V buoyant, is equal to rho liquid times V immersed. Yeah, V immersed. We replace V displaced liquid by V immersed times G. Okay, and then we are going to use this one as a formula for buoyant force. Buoyant force of water and other liquids is a direct result of the dependence of liquid pressure on depth. Yeah, maybe you asking, if there is buoyant force in the liquid, and then how about the effect, yeah, effect from the liquid pressure? Because before we have learned about liquid pressure, there is P, and then the object has area A, so should be liquid force there. But we can learn from this paragraph that the lifting or buoyant force of the water and other liquids is a direct result of the dependence of liquid pressure on depth. Yeah, or in other words, the buoyant force here is because of or appear because of the pressure from liquid. If you see here the formulation, the first you have to learn from this figure. There is figure about cylinder, fluid, yeah, liquid. The cylinder has area A and then height L, and then it has depth from the surface. The top one is a H1 and then the bottom side is a H2, yeah. And then same with our discussion Pascal principle, the object will press from any directions, yeah. In here from up, from bottom. Actually there is others, yeah, there is others from left and right, but from left and right same, and then you can cancel. Yeah, we can cancel. And then there is from up and from bottom, okay, because different depth, yeah. P1 and P2. Okay, P1 and P2. Can you predict which one greater, P1 and P2? P2 is greater, right? Because deeper than P1. Okay, and then F net here, first from the P1 and P2. P2 is greater, so in here V up minus V down, this one V up. Yeah, remember the direction of force following the direction of pressure. F1, F2, V up minus V down, V1, and then sorry, F up minus F down. F is a P times A, P2 times A, F down is a P1 times A, and then you can do like that. And then P2 minus P1, rho GH, okay. And then there is rho here, yeah, rho liquid times G times H2 minus H1 times A. Okay, and then H2 minus L, H2 minus, and then H2 minus H1 is the L itself, yeah. If you subtract here, H2 minus H1 is L right here, L, yeah, L times A. Okay, L times A, L times area is a volume, and then you got F net here, raw liquid, volume immerse times G. This is buoyant force, yeah, buoyant force. Okay, so we can get the buoyant force from the pressure difference. Then if you try to see this figure 1.21, yeah, if we have object, for example ball, inside the fluid, inside the water like that, so we can draw the free body diagram. Acting on object inside the water, there is a wake of object, obviously, and then buoyant force, yeah. This is important for you, that there is no buoyant force inside the fluids. Okay, buoyant force we have learned raw liquids, yeah, raw liquid. Why raw liquid? Because the force acting on object is done by liquid, so the raw here is raw liquid times V. V is a volume immerse times G, and then wake also have this formulation, but the difference is the raw here is a raw object, yeah, raw object, not raw water. There is important paragraph here, yeah. If the wake more than buoyant force, yeah, if the wake more than buoyant force, this one greater than buoyant force, the object will sink. Will sink. If the object sink, if the wake greater than FB, the object will sink. Object sink right here. In here it's when wake greater than FB. If the wake equal to FB, the object remains in the same position, yeah, or flying like that. If in the middle, at the middle, wake equal to FB. And finally, if the wake less than FB, the object rises upward to float. If the object float like that, it means here that the FB is a greater than wake. Okay, now consider an object completely underwater. V immerse equal to V object like that, yeah. V immerse equal to V object. We bring to the formula wake equal to F buoyant, yeah, V equal to F buoyant, let's say like that. And then wake is M times G, mass object times gravitational acceleration. F buoyant is rho Vg, rho of liquid, volume immerse, and G, we can cancel the G directly. In here, M, mass of object is equal to rho object times V object, volume object. Rho liquid times V immerse. And then in these conditions, if volume immerse equal to volume object, we can cancel directly like that. And then rho object equal to rho liquid. Before we learn how, if object sink and then object flying and then object floating, we use the term of wake and FB, yeah, wake and FB. In here we can use the density. If the density of object less than the density of liquid, the object will float. If the density of object equal to density liquid, the object will flying or flying, yeah. Object stays where it is left, or other set is flying, like flying. Okay. If the density of object more than density of liquid, then the object sink to the bottom of the liquid. Okay. For example, we have two different example right here. If I have water and then I have ball of metal. This is ball of metal. Ball of metal, rho metal is greater than row of water. Yeah, this is water, so the object will sink. Okay, the object will sink. If I have this one container containing water, and then I put something here, for example I put cork. We know density of cork less than density of water, so the cork will float. Okay, I think this one easy to understand. Now we discuss about floating object. Have two spheres in figure 1.22 here are made of different materials, okay, such as wood and cork. Okay, the spheres both float in the same liquid, should be sphere, yeah, should be here, and have the same mass. On which sphere does the water act with greater force? We have two objects, cork here, and then this one is a wood, and then float in the same liquid. And then which one greater, F1 here or F2 right here? Okay, also the same for the second conditions. If we have ring like that, the object different material also, and then also there is buoyant force acting on the objects, F1 F2, which one greater? In here the force acting on object is equal. Why equal? Because the volume immersed here are equal. Okay, buoyant force Fb equal to rho of liquid volume immersed ng. There is no density of object, yeah, but the density of liquid. Volume immersed, if volume immersed same, and the buoyant force same. Okay, now we can say in here, we can answer here that the spheres both fall in the same liquid and the mass. On which sphere does the water act with a greater force? No one, because F1 Fb1, yeah, equal to Fb2. Okay, the buoyant force of water on both spheres must be equal, yeah, and the buoyant force of water both spheres must be equal. Yeah, you can read by yourself here. Okay, and then when we try to solve problem about floating object, we can also using concept of equilibrium. If the object floats like that, we have wake, and then we have Fb, yeah, and then if the object at rest like that, it means that the floating means wake equal to buoyant force. Wake equal to Fb. Maybe you asking, before we talk, if the wake equal to Fb, the object is flying, not floating. How to explain that? Okay. In here, the Fb is different with the flying object. If flying, yeah, flying wake also equal with Fb, but Fb here is a maximum Fb. When the maximum Fb reach, when the volume immersed equal to with the volume object. But in the floating here, the Fb is not maximum Fb. Yeah, why? Because the volume immersed only this one, not all the volume of object immersed. You have to define you have to understand the differences. Okay, the difference between flying, Fb here is a maximum Fb, but for floating, when the wake equal to Fb, Fb here is not maximum Fb. It's not maximum Fb because the volume immersed is not all the full body object, but a part of it. Okay. If you try, you can try. If you try to push the object until the object completely immersed, if you try to push object, you give force from above, and then object completely immersed. And then after that you put your hand away. For example, put your hand away, and then the object will move up and floating. Okay, why? Because when you try to when the object completely immersed, yeah, by your hand, in here the FB greater than wake. Okay, FB greater than wake, which FB maximum FB greater than wake, and then the object move up like that and then start floating again. In here the object floating. Why? Because the wake equal to the FB, but it's not maximum FB, but FB that with the volume a part of it, yeah, not maximum FB. But if you try to push it like that, it means that the FB is maximum. After you release, after you put your hand away, the object will move up like that. Move up, because when the completely immersed, the FB greater than wake. Okay, when at the top of bottom, FB equal to wake, but FB here is not maximum FB, but FB a part of it, yeah, because the volume immersed this one only. Okay, you have to know about this. We try to solve one example. An object weighs 120,000 Newton in air, okay, and 80,000 Newton when completely immersed in the water. Okay, like that, become 80 kilonewton. Mentioned in figure. What is the density of object? Okay. From here directly we know there is buoyant force acting on the object is a 40,000, yeah, 40,000. I have another symbol for this. Okay, the wake on air is the true wake. We can use W only, and then wake on the water is we can use symbol W prime. W prime here is a apparent wake, the wake object in the liquid, yeah, apparent wake. How to find the buoyant force? FB is equal to wake minus apparent wake. Okay. The object loses 40,000 Newton when it is fully immersed in water. The force acting on the object as shown in figure 1.25. Yeah, here there is wake, okay, and then buoyant force inside the liquid, and then there is tension, yeah. The tension rate 80 kilonewton, so the buoyant force itself should be 40 Newton, yeah, 40 Newton. You can read F up equal to F down, okay, because the object at rest here, F buoyant, the move up, plus T is 80,000. The tension here, so the scale read the tension, yeah, the scale read the tension, or W prime, no problem. And then 40,000. This is the same if you want to find the F buoyant equal to wake minus wake prime. The wake in air, the true wake is 120 kilonewton minus the apparent wake 80 kilonewton. The result will be 40 kilonewton. Easy. After that, after we know the buoyant force, to find out the density, it is easy. You just using buoyant force equal to rho Vg, rho liquid, V immersed times G, and then the volume immersed is equal to F over rho times G, yeah, 40,000 over 1,000 times 10, and then you got the volume immersed 4 meter cube. The volume immersed, if you see, is equal to the volume of object, yeah, because full body object immersed, yeah, and then the rho of object mass over volume 12,000 kilogram over 4, so the density of object is 3,000 kilogram over meter cube. What percent of the total volume of a piece of ice will float on the surface of water? Density of ice and water are 900 kg per meter cube and 1000 kg per meter cube. respectively. Yeah, from the density we know that the density of ice less the density of water, and then the ice will float. And then this one, the picture, we have to find the percent of the volume of ice will float. Yeah, so the volume of ice above the surface of water. Okay, first we draw the free body diagram. There are F buoyant like that and then wake like that. Because of the system in equilibrium, F buoyant equal to wake. Okay, F buoyant raw liquid, V immerse, and then for the wake, M times G, M here density of object times volume of object times G. We can cancel the G directly, and then volume immerse over volume object equal to raw object over raw liquid like that. And then this ratio hold not only for this problem but for all objects floating in a liquid, substituting the numerical values. Volume immerse, then row of ice 900, row of water 1000, 0.9. It means 90%. Yeah. So 90% of volume of ice is immersed in water. Therefore, 10% must be floating above the water surface. Okay, let's continue with the solving problem regarding to the Archimedes principle. Okay, number 1, the buoyant force acting on an object completely immersed in a liquid is 1.8 Newton. What is the density of the liquid if the volume of the object is 225 cm3? Okay, we are looking for the density using formula from buoyant force. Fb equal to rho of liquid G time V, volume immerse. Yeah, volume immerse. Okay, we looking for the density, so the density of liquid equal to Fb over G times volume immerse. Fb already in SI unit, and then the gravitational acceleration also, but the volume immerse here should be in meter cube. 225 centimeter cube, we have to convert it become meter cube. Okay, centimeter to meter, move up two steps, and then divided by 1 million, because this one in cube, or times 10 power minus 6. Yeah, so in here become 225 10 power minus 6 meter cube. Okay, we put right here 1.8 over 10 times 225 10 power minus 6 meter cube. Okay, this one cancel, become minus 5. Okay, this is move up 1.8 10 power 5 over 225 equal to, we calculate right here. Let's take 1800 times 10 power 2 over 225. Okay, 1800 divided by 225. 8, yeah, 800 kilogram over meter cube. Number 2, the weight of an iron block is 790 Newton. Okay, what is the apparent weight of the same block when it is completely immersed in water? The density of iron is 7,900 kilogram per meter cube. The weight of an iron block, okay, the weight is 790 Newton. If the weight completely immersed on the water, or apparent weight in the water, yeah, how much? Okay. Apparent weight equal to the true weight minus buoyant force. Okay, and then we have the weight. Let's calculate 790 minus buoyant force is a raw liquid, G volume immersed. 790 minus raw liquid, yeah, not density of iron, raw liquid. This one water, 10 power 3 times 10. Okay, and then the volume immersed, because of the density of iron is greater than density of water, so this one completely immersed in the water. Okay, and then you have to find the volume immersed. If the volume immersed right here, volume of the object equal to mass over density. Okay, the mass of object here from this weight is a 79 kilogram. Then the density 7,900. Okay, so the volume is a 10 power minus 2 meter cube. Okay, right here 10 power minus 2. Okay, 790 minus this one minus 100, yeah, 100 is a 690 newtons. So this one apparent weight, yeah, the weight of iron block in water. Next, the object in the figure is made of a material of density 3000 kg per meter cube. Okay, what is the tension in the rope which suspends the object? Then it is completely immersed in water. The mass of the object is 200 kg. Tension here same with the apparent weight, yeah, same. The weight of object in the water. Okay, we have here density of object 3000, and then the mass of object is at 200 kilogram. We're looking for the W prime. Apparent weight equal to weight, the true weight minus FB. Weight minus FB is a row of liquid. Okay, G, and then volume immersed. Weight here from the mass of object, so the weight is at 2000 minus raw liquid in the water, yeah, in the water 10 power minus 3 times 10 times volume immersed. Right here is a we're looking for the volume immersed. We have the mass of object, we have the density of object, so the volume here is the mass over rho object, yeah, 200 divided by 3000. If we use fraction, no problem, 2 over 30 meter cube, 2 over 30. Okay, so 2000 minus cancel 2 divided by 3, okay, times 1000 become 666, let's say like that. So this one 2000 subtract by 366, 1334 Newton. So this one the tension or the apparent weight, the weight of object in the water. Number 4, a wooden block floats over water with 0.08 meter cube of its volume under the surface of the water. Okay, what is the mass of the block? Okay, let's say this one container containing water, and then there is a block right here, and then the volume of object above the surface, yeah, the volume immersed here 0.08 meter cube. what is the mass of block? Okay, so in here the weight, we can draw the free body diagram. There is weight and then there is FB, yeah, FB like that. And then object in equilibrium, so the weight equal to FB, but it's not maximum FB, yeah. You have no mass of block M times G. Here rho liquid, G volume immersed. Okay, we're looking for M. We cancel for G, so the mass of object equal to rho liquid, in here water 1000, volume immersed is a 8 times 10 power minus 2 meter cube, so the mass is a 80 kilogram. Number 5, a large wooden block of mass 1100 kg is partially floating on the water. What is the volume of block of wood which floats? We don't know what is this. What is the volume of block of wood which floats? Floats, yeah. So but I understand what does it mean. We're looking for the volume above the surface, yeah. Surface of water. Okay, we know the mass of wooden block 1800 kilogram, and then the density of wooden block is a 600 kilogram over meter cube. We are looking for its volume above the surface. Okay, we have wooden block. This is container containing water, wooden block like right here, then volume immersed, and then we're looking for this one, volume above the surface, yeah, VA, let's say like that. In here the weight in equilibrium, because the weight equal to with FB, weight equal to with FB. Okay, the weight of this wooden block, we have the mass times G, mass times G equal to rho liquid G, and then volume immersed. We cancel for G. We have the mass of object 1800 kg equal to the rho of liquid water 1000 times volume immersed. Okay, we move right here. V immersed will equal to 1800 divided by 1000, 1.8 meter cube. This one the volume of object below the surface. Okay, below the surface. We have to find the total volume of object. This is the volume of object equal to mass of object divided by rho of object. Okay, object here is a wood, yeah, wood. 1800 divided by 600 is a 3 meter cube. If volume immersed 1.8, so volume above is a 3 minus 1.8 is a 1.2 meter cube. Okay, that's all our explanation and solving problem today. Don't forget to like, share and comment for this video, and then subscribe my channel. Also turn on the notification for updating other videos from me. Thank you. Assalamualaikum warahmatullahi wabarakatuh.